This is chapter 10, Chemical Bonding. By the end of this chapter, you will be able to write Lewis structures for elements, write Lewis structures for ionic compounds. You will use Lewis theory to predict the chemical formula of an ionic compound. You'll be able to write Lewis structures for covalent compounds. Also, you will learn how to write resonance structures, predict the shapes of molecules, and determine whether a molecule is polar or not. So let's start by talking about the bonding theories. Bonding theories predict how atoms bond together to form compounds. They predict what combination of atoms form compounds and what combinations do not. For example, bonding theories predict why table salt is NaCl, sodium chloride, and not NaCl2, and why water is H2O and not H3O. So we're going to learn how to predict those structures and why we have each of them is represented by NaCl, for example, for table salt, and water, H2O. So the bonding theories explain the shapes of molecules, which in turn determine many of their physical and chemical properties. So we represent electrons as dots and draw what are called dot structures or Lewis structures to represent molecules. These structures have tremendous predictive power. Lewis theory can determine whether a particular set of atoms will form a stable molecule and what that molecule might look like. So let's do some examples. In Lewis theory, the valence electrons of main group's elements are represented as dots surrounding the symbol of the elements. The result is called a Lewis structure or a dot structure. Remember that the valence electron is also the number of the main group of which each element is part of. So as mentioned, the number of valence electrons for any main group element is equal to the group number of the element, with some exception, as for example helium, that even though it's in the 8th group, but it has 2 valence electrons. So we can also obtain those valence electrons by the electron configuration of the element. This one is the electron configuration of oxygen, 1s2, 2s2, 2p4. And this basically are the 6 valence electrons for oxygen. So the Lewis structure for oxygen will be something like this. We use the symbol of the element, oxygen, O, and we draw 6 electrons around the oxygen. We're going to use just 4 sides, okay, the top, the bottom, the left, the right. Those are the 4 sides that we're going to use to distribute those electrons. So we're going to start by putting one here, 1, 2, 3, 4, and then we start to pair them, 5 and 6, okay? So we can have a lone pair like this here, another one like here, and 2 electrons by themselves, or this pair can be in this side and 1 electron here, or it doesn't matter. We have a lot of different ways that we can represent it, but at the end we need to have two lone pairs. These are lone pairs, and 2 electrons alone around the oxygen. And there we will have our 6 electrons, and remember that oxygen is also part of the family group number 6. Each dot represents a valence electron. The dots are placed around the element's symbol with a maximum of 2 dots per side. Although the exact location of dot is not critical, here we fill in the dots singly first and then pair them, with the exception of helium described shortly. So here we have, for example, lithium has just one, we're going to put one here. Beryllium is a family 2, so we can put one here or one here, or we can put one here in the top and another one in the left, or in the top and the bottom. It doesn't matter, but the important thing is that we're going to have 2 electrons around beryllium. Boron we have 3, carbon we have 4. Okay, so remember that we need first to put the individual, and once we have the 4 sides complete, then we start to pair them, as we can see here for nitrogen. Nitrogens are family 5, so we start with 1, 2, 3, 4, and we need to add more and more, so 5. Again, this lone pair could be in the right side and the left side and top and the bottom. It doesn't matter as long as we have one lone pair and 3 electrons alone. Oxygen is from family 6, so we have 2 lone pairs and 2 electrons alone. And we have fluorine here with family 7, so we have 3 lone pairs and 1 alone. And neon is family 8, so we have 8 electrons, 4 pairs of lone pairs around neon, and that will make the 8. Lewis structures allow us to easily see the number of valence electrons in an atom. Atoms with 8 valence electrons, which are particularly stable, are easily identified because they have 8 dots and octet. Okay, so that's known as octet. So neon here is the only one that has that octet. So let's write the Lewis structure for phosphorus. Phosphorus is family 5. Okay, so that means that has 5 valence electrons. So we need to represent those 5 electrons as dots around that symbol of phosphorus. So we can write that like this. Or again, this lone pair could be in the top or on the left or on the bottom, and the other 3 around the symbol. Okay, so it doesn't matter that it doesn't have to be in the right side, this lone pair, or in the left side and the bottom. So it's up to you. So helium is an exception. Its electron configuration and Lewis structure is this one, or are this one. This is the electronic configuration, 1s2, and helium, we're going to have 2 electrons in creating a lone pair. The Lewis structure for helium contains 2 paired dots, or a duet. For helium, a duet represents a stable electron configuration. This is the only element that's going to have a duet without having lone pairs. All the others needs to have lone electrons first, and then we start to pair them. Okay, but helium is the only one that's going to have a lone pair electron without a lone electrons around the helium. So Lewis' theory of chemical bonding. A chemical bond involves the sharing or transfer of electrons to attain stable electron configuration for the bonding atoms. So here a chemical bond is going to be formed by sharing electron or transferring those electrons between those atoms. So if the electrons are transferred, the bond is an ionic bond. So whenever you transfer electrons from one element to another one, that is going to produce an ionic bond. If electrons are shared, the bond is called a covalent bond. In either case, the bonding atoms attain stable electron configuration. That means that they're going to have 8 electrons around, creating the octet. Okay, so that's really important. The idea of this bonding theory is that all the elements or atoms will be stable by gaining that electron configuration of 8 electrons around each symbol. A stable configuration usually consists of 8 electrons in the outermost or valence shells. This observation leads to the octet rule. In chemical bonding, atoms transfer or share electrons to obtain outer shells with 8 electrons. The octet rule generally applies to all main group elements except hydrogen, lithium, and beryllium. Each of these elements achieves stability when it has 2 electrons or a duet in its outermost shell. But this will be when they share or when they transfer electron, okay, as different as helium. Helium by itself has that duet. These 3 elements, they will gain that structure by sharing or transferring electrons to them, okay? Also, another important thing is that to create that 8 electrons around here, some of the elements will gain 1 or 2 electrons to have those 8 octet rule around that element, or others will lose electrons. So in that way, when they lost those electrons, they will have 8 electrons because they will go to the lowest or the previous level. Okay, so we're going to see an example in a few seconds to explain a little bit more of that. So loose structures of ionic compounds, electrons transferred. When metals bond with nonmetals, we are creating a ionic compound, and the electrons are transferred from the metal to the nonmetal. Okay, so remember that metals will always produce cation. That means that those element metals will release an electron. Okay, so when they release an electron, at least one, you're going to create a positive charge that is known as a cation. And remember that all the metals are at the left side of the periodic table, while the nonmetal is on the right side. Those nonmetals, they tend to gain electrons to produce an ion. Okay, so whenever you have a metal with a nonmetal, you will produce an ionic compound, and the electrons that are between them, they're going to transfer it. They are not sharing those electrons. The metal becomes a cation and the nonmetal becomes an anion. The attraction between the cation and anion results in an ionic compound. In Lewis' theory, we represent this by moving electron dots from the metal to the nonmetal. Always, the metals are the ones that are going to give or release those electrons, while the metals always are going to obtain or receive those electrons. So for example, let's see potassium chloride. Okay, these are the structure of potassium. Potassium has one electron, valence electron, because it's in family 1, while chlorine is in family 7, so they have 7 electrons. So what happened here? Potassium can release these electrons to chlorine, so now chlorine will gain the octet. Okay, it will have 8 electrons around, and also because this one is neutral, when they gain that electron, it's going to be a negative, it's going to be a cation. While potassium right here is neutral, but when they release that negative charge, they will gain a positive charge, and also now the valence electrons are the shell before the one that we have here with potassium. So in that way, okay, when they share that electron, transfer that electron to chlorine, they will gain a positive charge, while chlorine will gain a negative charge. So let's see of magnesium oxide. Magnesium has 2 electrons, valence electron, because it's in the family number 2, while oxygen has 6. So what can happen here? It could happen here. One electron can be transferred to this oxygen, and also this can be transferred to the oxygen, because if you just transfer one, we're going to have 7, so they need another one. So that's why magnesium can release those 2 electrons. In that way, they will gain a charge of positive 2 because they release 2 electrons. While oxygen, they accept those 2 electrons, they will gain a negative 2 charge. Okay, so that in MgO, magnesium oxide, magnesium loses its 2 valence electrons, resulting in a positive 2 charge, and oxygen gains 2 electrons, attaining a 2 minus charge, and also the octet. Here we have the representation: magnesium plus 2, the oxygen, the anion with the octet. Most of the time they'll use the bracket to put that oxygen inside. And it's a minus 2 because they gain those 2 electrons. While magnesium, they release those 2 electrons, so that's why it's positive 2. So Lewis' theory predicts the correct chemical formulas for ionic compounds. Consider the ionic compound formed between sodium and sulfur. So the Lewis structure for sodium is Na1 because it's family 1, so we have just 1 electron, while the sulfur has 6 because it's a family 6. So that means that how many electrons does sulfur needs to complete the octet? It may need 2 more, but sodium can just release 1 electron because sodium is a family 1. So that means that how many sodium do we need? So we need 2 sodium. So in that way, each sodium will release 1 electron, okay? And each sodium will have a charge of plus 1 because each sodium release 1 of those electrons, okay? While sulfur receive 1 electron from one sodium and another one from the other sodium. So they're gain 2 electrons, going to be a minus 2. So that's why the combination between sodium and sulfur is Na2S. That's the formula. That's the chemical formula for the sodium sulfide. Okay, so we have here the sodium with a positive 1 charge because each sodium release 1 electron, each of them, even though the total will be 2 electron transfer from all the sodium, but each one release 1 electron, whilst sulfur will receive both electrons from sodium, gaining a charge of -2. And this is the formula, Na2S. That's why it is Na2S. So let's talk now about the covalent Lewis structure. Okay, in this ones, the electrons are shared. So in the ionic Lewis structures, the electrons are transferred. Here we share electrons. What are the covalent Lewis structures? Okay, so this most is gonna you're gonna see this when you are doing compounds between two nonmetals. Okay, between two nonmetals, you're gonna have always a covalent bond. Okay, between them. So when nonmetals bond with other nonmetals, a molecular compound results. Molecular compounds contain covalent bonds in which electrons are shared between atoms rather than transferred. So that's a really big difference between the ionic compounds with the covalent compounds. In the Lewis theory, we represent covalent bonding by allowing neighboring atoms to share some of their valence electrons in order to attain octet or duets for hydrogen. Okay, in the case of hydrogen, you're not going to have an octet, you're going to have duets. Hydrogen and oxygen have the Lewis structure of H with 1 dot, okay, because it's from family 1, while oxygen, as we mentioned before, we have 6 electrons around it. So oxygen may need 2 electrons to complete that octet. So each hydrogen will release or we shared 1 electron. Okay, so we may need 2 hydrogens so we can complete that octet around the oxygen. So that's why water is a combination of 2 hydrogens and 1 oxygen. So in that way, this hydrogen has 2 electrons around a duet and is pretty stable because that also the configuration of helium as well as this hydrogen. This hydrogen has 2 electrons around, while the oxygen will have 8 electrons around, completing that octet. And also, it is important to understand that these 2 electrons are shared between these 2 atoms in a covalent bond, and these 2 electrons are shared by also these 2 elements or atoms, creating a covalent bond. So between the oxygen and the hydrogen, we're going to have 2 covalent bonds and 2 lone pair electrons. So the shared electrons, those that appear in the space between the atoms, count toward the octet of both of the atoms, as I mentioned before. For oxygen, we're going to complete the octet, while for hydrogen, we're going to complete the duet. And that will bring a lot of stability for this molecule of H2O or water. So the electrons that are shared between 2 atoms are called the bonding pair. And the electrons that are only on 1 atom, as for example this and this electrons, they are called lone pair or non-bonding electrons. Okay, so these are lone pair of electrons and these are bonding pairs of electrons. Bonding pair electrons are often represented by dashes to emphasize that they are a chemical bond. So instead of 2 electrons between the oxygen and the hydrogen, sometimes we can represent that by a dash. Okay, and this, remember that whenever you see 1 dash of this, you're gonna see 2 electrons always. Okay, so here we have 2 electrons between this hydrogen and this oxygen, 2 electrons between this oxygen and hydrogen because we have another bond here. So we have 2, 4, 6, 8. 8 electrons around the oxygen to complete that octet. The Lewis theory explained why the halogens form diatomic molecules. So for example, chlorine. Chlorine has 7 electrons around. So if we have, for example, 2 atoms of chlorine, they're paired together and they can attain the octet because each of them are going to share 1 electron with the other one. And in that way, you create here a a bond between those atoms, okay? And around this chlorine, you will have 8 electrons, and around this chlorine, you will have 8 electrons. Or also, you can represent these two uh, pair bonds electrons as a dash or as a bond per se. And always, once again, this here you can see two. Whenever you see a dash, you're gonna see 2 electrons. So 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons around each of the chlorine. When we examine elemental chlorine, we find that it exists as a diatomic molecule, just as the Lewis theory predicted. The same is true for the other halogens. For chlorine, fluorine, iodine, for all of them are basically the same. The Lewis theory predicts that hydrogen should exist as H2. Why? Because hydrogen has just 1 electron, and if it's going to create a compound with another hydrogen, well, they're going to share those 2 electrons between them, okay? And we're going to create a duet, or basically a bonding pair electron between them. So we can write also a dash between them, and we're going to have the structure for H2 or hydrogen as it exists in that nature. The Lewis theory is correct. In nature, elemental hydrogen exists as H2 molecules. So what about, for example, oxygen? Oxygen has 6 electrons around, it's our family 6. So if we have another oxygen, what we can do between them? We can share maybe this electron with this electron to create one bond, okay? But if we do that, we're going to have 2, 4, 6, 7. We still have missing 1 electron to complete that octet. But we have 1 electron here and also here. So maybe we can share this, and also share this and this. So we're going to share 4 electrons between those oxygen, something like this. But remember that you can create a bond by sharing just 2 electrons. So we have here one single bond here and another single bond here. So that creates a double bond. So we can represent that also as this one, okay, where each dash or line is represented as 2 electrons. So we are sharing between those 2 oxygen 4 electrons. So we have 2, 4, and 4 here, 8. We have 4, 6, and 8. So each of those oxygen has their octet. Here, each oxygen, as I mentioned, now has the octet because of the additional bonding pair counts toward the octet of both oxygen atoms. So what about nitrogen? Nitrogen is from family number 5. So we have this. So if we share this 2 electrons between them, we're going to have 2, 4, 5, 6. So we may need to share also this with this, and also this with this electron. So we're going to have 6 electrons between those 2 nitrogens. So that means that we're going to have something like this. Okay, we share this with this one with this one, and this and the left, far left, to this with the far right, but they're going to be sharing between them. Okay, remember that we are creating bonds between atoms. That's why we're going to share those 6 electrons between these 2 nitrogen here. So we're going to have 1, 2, and 3 single bond. So there's going to be a triplet or a triple bond. So we're going to have a triple bond here. In each bond, we're going to have 2 electrons. So we have 2, 4, 6, and 2, 8, as well as 2, 4, 6, and 2, 8. So we're going to have 8 electrons here and 8 electrons around this nitrogen. Each of those nitrogens, as we represented here or here, has 8 electrons around. So it completes the octet. So when 2 electron pairs are shared between 2 atoms, the resulting bond is a double bond. In general, double bonds are shorter and stronger than single bond. For example, the distance between the oxygen nuclei and an oxygen-oxygen double bond is 121. In a single bond, it is 148. I said 121 picometer. and the single bond, it will be 148 picometer between them. Okay, so the double bond is shorter than the single bond. And the triple bonds are even shorter and stronger than the double bond. So the distance between nitrogen nuclei in nitrogen-nitrogen triple bond is 110 picometer. Okay, so this one is shorter than even though the double or the single bond. The double one is 124, so this one is 110, is shorter, and also is stronger than the double bond. When we examine nitrogen in nature, we find that it exists as a diatomic molecule with a very strong short bond between the two nitrogen atoms, and they are a triple bond, as we mentioned before. The bond is so strong that it's difficult to break, making nitrogen a relative unreactive molecule. So let's write structure for covalent compounds. I'm going to first show you some rules, and then we're going to do some examples. So first, write the correct skeletal structure for the molecule. The skeletal structure shows the relative position of the atoms and thus not include electrons, but it must have the atoms in the correct position. For water, oxygen is in the central atom and the hydrogen atoms are terminal atoms at the ends. The correct skeletal structure is HOH. Another hint is that it's like a Lego. So the piece of Lego that you have that can create more bonds, you're going to put that in the middle because oxygen has 6 valence electrons. So we have 2 lone pairs and 2 electrons in each side that can create 2 more bonds. While hydrogen is from family 1, so hydrogen can create just 1 bond. So that's why hydrogen can be in the middle of the molecule. So that's why oxygen is in the middle and hydrogen is going to be in the ends. The only way to absolutely know the correct skeletal structure for any molecule is to examine its structure in nature. So we need to remember 2 guidelines for writing the correct skeletal structure. First, hydrogen's atoms will always be terminal. Since hydrogen requires only a duet, it will never be a central atom because central atom must be able to form at least 2 bonds and hydrogen can form only 1. And second, many molecules tend to be symmetrical. So when a molecule contains several atoms of the same type, this tends to be in terminal position to create that symmetrical molecule. This second guideline has many exceptions. In cases where the skeletal structure is unclear, the correct skeletal structure is usually provided. Second, we need to calculate the total number of electrons for the Lewis structure by summing the valence electrons of each atom in the molecule. The number of valence electrons for any main group element is equal to its group number in the periodic table, and this represents the valence electrons. If we are writing a Lewis structure for our polyatomic ion, the charge of the ion must be considered when calculating the total number of electrons. So if we're writing a polyatomic ion and that ion has a negative charge, you may add 1 electron to the pool of electrons that we count for each of the atoms. Now, if the polyatomic ion is positive, we need to subtract 1 electron for each positive charge of the pool of the electrons that we have or calculated for the atoms itself. And third, we distribute the electrons among the atoms, given octets or duets for hydrogen to as many atoms as possible. Begin by placing 2 electrons between each pair of atoms. These are the minimal number of bonding electrons. Then distribute the remaining electrons first to the terminal atoms and then to the central atom, given octets to as many atoms as possible. And number 4, if any atoms lack an octet, form double or triple bonds as necessary to give them octets. Do this by moving lone pair electrons from terminal atoms into the bonding region with the central atom. So, CO2. We need to follow the symmetrical guideline, write the skeletal structure. Oxygen can create just 2 bonds, while carbon can create 4. So that's why we need to write carbon in the middle and oxygen in both sides, ends. And now we need to calculate the total number of electrons for the Lewis structure by summing the valence electrons of each atom in the molecule. So carbon has 4, number of valence electrons of carbon is 4, and oxygen is 6, but we need to multiply by 2 because we have 2 oxygen. So we have 4 electrons plus 2 times 6 electrons for each oxygen. We're going to have a total electrons of 16. So we need to distribute those 16 um, electrons around each of the elements. Okay, so we have between oxygen and carbon 2, between carbon and oxygen 2, we use 4 of the 16, so we have 12 that it can be shared. So we can put here basically 2, 4, 6, 8, 10, 12. Okay, so we use all those electrons around those elements. But we can observe that between around this oxygen we have 8 electrons, around this oxygen we have 8 electrons, but around carbon we just have 4 electrons. So we can share 2 lone pair or 2 of this electrons between this carbon and carbon, and 2 between this carbon and carbon. So in that way we can create basically a double bond in each side of the carbon between each oxygen. So now we have here the oxygen with 8 electrons around the oxygen, carbon with 4 and 4 electrons around it, and oxygen, we have 4 here and 4 here, 8. So this is the representation of CO2. So let's write now a Lewis structure for a polyatomic ions. Remember that when we have an ion, we're going to have a charge. And if we have an ion with a negative charge, we're going to add 1 electron to the total number of valence electrons for each atom. And if the ion is positive, we're going to subtract one number per each charge of the ion. So let's see this example. Write the Lewis structure for polyatomic ions by following the same procedure, but pay special attention to the charge of the ion when calculating the number of electrons for the Lewis structure. Add 1 electron for each negative charge and subtract 1 electron for each positive charge of the ion. Show the Lewis structure for a polyatomic ion within brackets and write the charge of the ion in the upper right corner. So let's write this Lewis structure for Cn-1. We begin by writing the skeletal structure. We just have 2 atoms, so that means that we're going to have the carbon on the left and the nitrogen on the right. And we need to calculate the total number of electrons for the Lewis structure by summing the number of valence electrons for each atom and adding 1 for the negative charge. Because as the ion is negative, we're going to add 1 more. So carbon is 4, nitrogen is 5. Okay, so the number is going to be 4 plus 5 plus 1, that is due to the charge of the ion. We're going to have 10 electrons, a total of 10 electrons to distribute between these 2 atoms. So let's write first the bonding electrons between them. We have 2, so we have 8 more, so we can distribute between them. So we're going to can put 2 pairs in the carbon, 2 pairs in the nitrogen, but that means that we're going to have just 6 electrons between them. So now we can create a multiple bond between them by sharing those electrons between those 2 atoms. So since neither of the atoms has octet, move 2 lone pairs into the bonding region to form a triple bond, given both atoms octets. So in that case, then we go ahead and close the Lewis structure in brackets and write the charge of the ion in the upper right corner. So we have here, okay, we're going to share 2 lone pairs, so we can have 6 between them, and 2 more, we have 8. So we have 8 electrons around this carbon and 8 electrons around this nitrogen. So that means that in this structure, we're going to have a triplet or a triple bond between the carbon and nitrogen with one lone pair in each of the atoms. So in that way, we are going to have 8 electrons in each, completing the octet rule. And we're going to have to draw that inner bracket, and the charge is going to be outside, that is -1. So there are some exceptions to the octet rule. Lewis theory is often correct in its prediction, but exceptions exist. For example, the Lewis structure for NO, which has 11 electrons, is this one. So here we can see that we're going to have just a lone electron there. It is impossible to write a good Lewis structure for molecules with odd numbers of electrons. Yet some of these molecules exist in nature. In such cases, we write the best Lewis structure that we can. So we have here the nitrogen with just one electron, and this is how it exists, NO, nitric oxide, in nature. Another significant exception to the octet rule is boron, which tends to form compounds with only 6 electrons around boron rather than 8. So for example, here we have BF3 or BH3, and both of them, we can see that the boron has just 6 electrons, so it's lacked on the octet. So it doesn't have an octet around that one, but they are pretty stable. Okay, so we can have elements with less than 8 electrons that are stable as boron, and also we can have maybe some elements that has just 1 electron with an odd number of electrons around it. Also, molecules such as SF6 and PCl5 have more than 8 electrons around a central atom in the Lewis structure. Okay, so that is it's expanded. So we can hold more than 8 electrons. Okay, so these are referred as expanded octets. We mentioned them. We do not cover expanded octets here. Okay, so we just to give you an example that these are some exceptions. Some of them has more than 8, some of them has less than 8 electrons. In spite of these exceptions, Lewis theory remains a powerful and simple way to understand the chemical bonding. Now let's talk about resonance. When writing Lewis structures for some molecules such as SO2, we can write more than one good Lewis structure. Okay, begin with the skeletal. Let's do this one with the SO2. We have the oxygen, the sulfur in the middle, and oxygen in the right side. And we're gonna look for the electrons, valence electrons. We have 6 for each oxygen. And also for the sulfur. So at the end, we're gonna have 18 electrons that we're gonna share between, or we're gonna have this Lewis structure. So we're going to put the bonding electron between them. So from 18, we have 4 that we use, so we have left 14. And then we're going to distribute the remains around both oxygen. Okay, so we have 2, 4, 6, 2, 4, 6, 6 and 6, so 12, 16, and basically we have 16 around it. Okay, so we need to put 2 more electrons. So let's put that in the central atom. Okay, so we're going to have now 18 electrons around this structure, but we can see here that even though the oxygens, both of them has the octet complete, but the sulfur has just 6 electrons. So we can share one pair of those electrons, okay, between those oxygen and sulfur. As here, we can see we can take these 2 electrons and put it here, and we can produce a double bond between this oxygen and this sulfur. So now we're going to have 8 electrons around this oxygen, 8 electrons around sulfur, and 8 electrons around this oxygen. So this is one structure, okay, when we have the double bond between the left oxygen and the sulfur. But also we could form the double bond between the right oxygen and the sulfur, okay? The 2 structures are equally correct as Lewis structure. Both of them has 8 electron in this oxygen, 8 electron in this sulfur, and 8 in this oxygen. So we find that the molecules exist in nature as an average or intermediate between the 2 Lewis structures and neither one alone represent reality. So both of them are called resonance structure for SO2. Either one of the two Lewis structure for SO2 would predict the SO2 would contain two different kinds of bonds, one double bond and one single bond. When we examine SO2 in nature, we find that both of the bonds are equivalent and intermediate in strength and length between a double bond and a single bond. In nature, we find that the bonds are equivalent. We can account for this in Lewis structure by representing the molecule with both structure, and we call them the resonance structure, with a double-headed arrow between them. Okay, so that means that this structure is a resonance structure of this one. Okay, and this one is a resonance structure of this one. As you can see here, in each one you're going to have one oxygen with a double bond and two lone pair. Oxygen, double bond, two lone pair. Sulfur, three or one double bond, one single bond, and one lone pair. Sulfur, one double bond, one single bond, and one lone pair. And an oxygen with three lone pairs and one single bond, three lone pair and one single bond. So we have basically the same structure and the same elements, okay, of bonding around each of the atoms in both of them. This is called the resonance structures. The through structure of SO2 is intermediate between these two resonance structures.
Now I'm going to introduce you a concept that is known as the valence shell electron pair repulsion, or the VSEPR. This theory is going to help us to predict the shapes of molecules. This theory is based on the idea that electron groups that could be lone pairs, single bonds, or multiple bonds, including double bonds or triple bond, repel each other. So whenever we're talking about electron groups, we can find them as single bonds, double bonds, triple bonds, or lone pairs in the central atom. This repulsion between the negative charges of electrons group on the central atom determines the geometry of the molecule. So let's see an example here. Let's predict the shape of CO2, which has this Lewis structure, carbon in the middle, two double bonds at each side, and oxygen at the end of the molecule. The geometry of CO2 is determined by the repulsion between the two electron groups. In this case, we have one electron group here that is a double bond, and we have another electron here that is another double bond. So we have two electron groups on the central atom that is carbon. These two electron groups get as far away from each other as possible, resulting in a bond angle of 180 degrees, as we can see here, and a linear geometry for CO2. So that means that the shape for CO2 is linear. What about H2CO, also known as formaldehyde? So this molecule has three electron groups around the central atom. As we can see here, we have a double bond, that is one electron group, single bond and single bond, so we have three electron groups around the central atom. These three electron groups get as far away from each other as possible, resulting in a bond of 120 degrees and a trigonal planar geometry. So whenever we have one central atom with three electron domains or electron groups around, the molecular geometry is going to be, or the electronic geometry in this case, is going to be the trigonal planar geometry. If a molecule has four electron groups around the central atom, as does CH4 or methane, it has a tetrahedral geometry with bond angles of 109.5 degrees. So between each bond, okay, we're going to find an angle of 109.5 degrees. And here we have a central atom, and around it we have four different electron groups. So that means that when we have four electron groups, that geometry is going to be a tetrahedral. A tetrahedron is a geometric shape with four triangular faces. Methane is shown here with both a ball and stick model, that is this one, and a space filling model that is in the right. We're going to show it in the next one. Yet the ball and stick models are often used to clearly illustrate molecular geometry. So here we have the ball and stick model, and the next one is the space filling model. And even though it doesn't matter which model you use, always the angle between the bonds is going to be 109.5. So the mutual repulsion of the four electron groups causes the tetrahedral shape. The tetrahedrons allows the maximum separation among the four groups. When we write the structure of CH4 on paper, it may seem that the molecule should be square planar with bond of angle of 190 degrees, but it's not planar, it's tetrahedral. So in this way, we can see that we can think that, okay, this is basically our square planar. The angle between them is 90 degrees, and it's true when you draw it this way, but in reality, the range is a tetrahedral one where the angle is going to be 109.5 degrees. In the three dimensions, the four electron groups can get farther away from each other by forming the tetrahedral geometry. Predicting the shapes of molecules with lone pairs on the central atom. Now, we saw before different examples where all the electron groups have atoms at the end of each bond, but maybe sometimes the central atom itself can has lone pair electrons. So what happened with that? The NH3 molecule has four electron groups. If we look only at the electron geometry, the geometrical arrangement of the electron group is tetrahedral. So we're going to talk about the electron geometry and the molecular geometry. So the electron geometry is when we focus and look at the arrangement of the electron groups. And in this case, it's tetrahedral. The molecular geometry is the geometrical arrangement of the atom is trigonal pyramidal for NH3. So NH3 is going to have a tetrahedral arrangement for the electron geometry, but a trigonal pyramidal for the molecular geometry. The lone pairs exerts its influence on the bonding pairs. The bond angles in NH3 are actually a few degrees smaller than the ideal tetrahedral angles. So we have here NH3, as we can draw the Lewis structure. Okay, we can see that we have 1, 2, 3, 4 electron groups. So that means that the electronic geometry is going to be tetrahedral. We're going to have 1, 2, 3, 4 electron groups. So remember, when we have 4 electron groups, the electron geometry is going to be tetrahedral. But if one of those electron groups is a lone pair, now the molecular geometry, as we can see here, is trigonal pyramidal. It's like a pyramid with 3 sides, so that's why we call it trigonal pyramidal. So we can have an electronic geometry of one shape and the molecular geometry of another shape. Methane, the one that we saw before, that was CH4, has an electronic and geometrical shape is the same, tetrahedral, both of them. But here we have an electronic geometry that is tetrahedral, but a molecular geometry that is trigonal pyramidal. What about water, H2O? If we look only at the electron geometry is going to be tetrahedral, but the molecular geometry is going to be bent. So the same thing, the lone pairs exerts influence to the bonding pairs, and they are a few degrees smaller than the ideal for tetrahedral. So here we have the Lewis structure for water, H2O, and we can see here that we have 1, 2, 3, 4 electron domains or electron groups. So that means that we're going to have a tetrahedral shape for the electron or electronic geometry. So here we have the tetrahedral shape for the electron geometry or electronic geometry for water, but the molecular geometry is going to be a bent. Okay, so the bent structure, we're going to find it in the molecule of water. Here we have like a summary of the table. Whenever we have, for example, 2 electron groups and both groups are bonding groups, the shape is going to be linear for the electron and the molecular geometry. If we have 3 groups, we're going to find, for example, if we find that all of the 3 groups are bonding, then the electron geometry and also the molecular geometry is going to be trigonal planar. But if we have 3 electron groups and one of them is a lone pair, we're going to have the trigonal planar for the electronic geometry, but the molecule is going to be bent. This one example, SO2, is an example of that. Three groups, or three electron groups, when we have two of them bonding and one lone pair. For when we have four, if the four of them are bonding groups, then the electronic and the molecular geometry are going to be tetrahedral. If one of them is a lone pair, the electron geometry is going to still tetrahedral, be tetrahedral, but the molecular is going to be trigonal pyramidal. And if two of them are lone pairs, the electron geometry is going to be tetrahedral, but the molecular is going to be bent. So, how we can use the VSEPR theory to predict the shape of the geometry of the molecules. So first of all, we need to draw a correct Lewis structure for the molecule. Second, we determine the total number of electron groups around the central atom. This is important. It's not around the atoms in the end of the molecule. It's in the central atom, because we can have a CO2. That CO2 has two oxygen as the end, and both of them has lone pairs, but those lone pair doesn't affect the structure of the molecule, because the carbon is the central atom and it doesn't have any lone pairs. It just have two double bonds, one with oxygen and the other one with the other oxygen. And we saw that CO2 is a linear molecule. So number three, determine the number of bonding groups and the number of lone pairs around the central atom. And number four, refer to the table to determine the electron geometry or the molecular geometry. So to represent the molecular geometries in the paper sometimes is a little bit hard, okay? Many chemists use this notation for bonds to indicate three-dimensional structure and two-dimensional on the two-dimensional paper. So for example, we usually use the line, okay, when the bond is in the plane of the paper. We're going to use the hashed lines when the bond is projecting into the paper, and we're going to use the wedge for bonds that are projecting out of the paper to try to give this three-dimensional structure in the paper. So whenever the bond is in the paper, in the plane of the paper, we're going to draw a straight line. When it's projecting into the paper or back to the paper, you're going to use the hashed lines, and when the bond is projecting out of the paper, we're going to use the wedge. Now let's talk about electronegativity and polarity. If you combine oil and water in a container, they separate into distinct regions. The question is why? Sometimes a water molecule causes them to bunch together into one region, expelling the oil molecules into a separate region. Here we have the Lewis structure for water, H2O. The two bonds between oxygen and hydrogen each consist of an electron pair, two electron shares between the oxygen atom and the hydrogen atom. As mentioned before, each of the single bonds, whenever you see a single bond, you need to also see two electrons. And in this case, those electrons are shared between oxygen and hydrogen, as well as these two electrons that are part of this bond. So this bond has two electrons that also are shared between oxygen and hydrogen. The oxygen and hydrogen atoms each donate one electron to this electron pair. However, they don't share them equally. The oxygen atoms takes more than its fair share of the electron pair. So that means that if we think of the two electrons being here sharing the middle, the oxygen for some reason pulled them more closer to them as a hydrogen. So you're going to have those electrons closer to hydrogen and being far away from the hydrogen. So the oxygen has something that can pull them more than the hydrogen. And that is called electronegativity. The ability of an element to attract electrons within a covalent bond is called electronegativity. Oxygen is more electronegative than hydrogen, which means that on average, the shared electrons are more likely to be found near the oxygen atom than near the hydrogen atom. And here we have a representation of how we can see that. So we have the oxygen here, the hydrogen here. The electrons are more closer to the oxygen than the hydrogen. So that's why the oxygen has going to have a partial negative charge. This symbol delta, okay, is going to represent the partial, and the negative was going to be partial negative. As the same thing, when you're removing those electrons from hydrogen, the hydrogen is going to feel more positive, and it's going to be a partial positive charge. Okay, so we're going to have partial negative or delta negative and delta positive or partial positive for the bond between this oxygen and this hydrogen, creating a dipole moment. Okay, there's a dipole moment because we are creating two dipoles, one positive and one negative. The result of this uneven electron sharing is a dipole moment, a separation of charge within the bond. And now we can talk about the polar covalent bonds. The covalent bonds that have a dipole moment are called polar covalent bonds. So that means that that bond between hydrogen and oxygen is a polar covalent bond. The magnitude of the dipole moment and the polarity of the bond depend on the electronegativity difference between the two elements in the bond and the length of the bond. For a fixed bond length, the greater the electronegativity difference, the greater the dipole moment and the more polar the bond. Okay, so that means that if we have a large difference between the electronegativity of the two elements that form that bond, then that bond could be classified as a polar covalent bond because it has a great dipole moment. So the value of electronegativity is assigned using a relative scale on which fluorine, the most electronegative element, has an electronegativity of 4.0. Linus Pauling introduced the electronegativity scale used here. He arbitrarily set the electronegativity of fluorine at 4 and computed all other values relative to fluorine. And here we can see basically the periodic table with the values for electronegativity. And as you can see here, we have 0.7, 0.8, 0.9. So it seems like it's basically increasing from the bottom to the top, okay? And also you can see 0.8, 0.1, 1.7, 1.8, it's increasing from left to right. So the trend in the periodic table is that the electronegativity increase from bottom to top and from left to right, making fluorine here, as we can see here, the most electronegative element of the periodic table. So what happens if we have two identical electronegativities? If two elements with identical electronegativities form a covalent bond, they share the electrons equally, and there is no dipole moment. So that means that if we think about the two electrons again between those two elements, the electrons are going to be in the middle of those two elements without creating those dipole moments at the end. For example, in Cl2, the two chlorine atoms shares the electrons evenly. This is a pure covalent bond, and the bond has no dipole moment, so the molecule is nonpolar. Okay, even because you don't have basically a polar bond, the molecule itself is going to be nonpolar. And here we have the Cl2, so the electrons are shared evenly between them, so you're not creating a dipole in neither one of the ends. So when we have a large electronegativity difference, we are creating covalent polar bonds. If there is a large electronegativity difference between the two elements in a bond, such as what normally occurs between a metal and a nonmetal, the electron is completely transferred and the bond is ionic. So if the difference is really large, it's going to be that large that the electrons are going to be basically all the time in one of the atoms, and the other one's going to lose those electrons. So in that way, we can create an ionic bond. So instead of creating dipoles, we are creating ions. Okay, you're not going to see any more dipole moments because you're not sharing those electrons. One of them is going to take those electrons for it, while the other one is going to lose them. For example, the sodium chloride. Sodium completely transfer an electron to chlorine. and this is an ionic bond. So you can see here that the electrons has been transferred completely to chlorine. That's why sodium is positive, and it's not partial, it's positive, and chlorine is negative. So remember that we're going to determine if the bond is polar or nonpolar by the difference in electronegativity of the two atoms that are creating that bond. So what happens if the difference is small? That means that if the difference is between 0 and zero point 0.4, the bond is a nonpolar bond or a pure covalent bond. Okay, you can use basically nonpolar or pure covalent. Most common is nonpolar bond. Okay, and if it's between zero point 0.4 and 2, that bond will be classified as a polar covalent bond. And if it's larger than 2, the difference between the two atoms or elements that are creating that bond is considered an ionic bond. Okay, so between 0 and zero point 0.4 is going to be a nonpolar bond. But the difference between 2 and zero point 0.4, if this is between these values, that bond is going to be a polar covalent bond. And if it's larger than 2, then the bond will be considered an ionic bond. So there is an interesting question because we need to classify the molecules if they are polar or nonpolar. And if we think of a polar molecule, that means that we need polar bonds. Okay, but the question is, if all the molecules that has polar bond, all of them are polar molecules, so does the presence of a one or more polar bonds in a molecule always result in a polar molecule? And the answer is no. Okay, a polar molecule is one with polar bonds that add together. They do not cancel each other to form a net dipole moment. Okay, so from each bond, we're gonna be watching if they can add, okay, those polarities to create that polar on the molecule, or that polar molecule. Okay, so if a diatomic molecule contains a polar bond, then the molecule is polar. For molecules with more than two atoms, it is more difficult to tell polar molecules from nonpolar ones because two or more polar bonds may cancel one and another. Okay, we're gonna see that in the next slides to explain a little bit more about why, even though you have polar bonds, the molecule could be nonpolar. So here we have an example. Consider carbon dioxide. What do you think about this bond between oxygen and carbon? This one is a polar or nonpolar bond. This one is a polar bond, and this side is more partial negative because oxygen is more electronegative than carbon. So it's going to be partial negative, and this one is going to be partial positive. What about this one? This bond is also polar because this is a partial negative. The oxygen is going to pull those electrons more than the carbon, and this is going to be partial positive. Okay, so each bond is a polar because the difference in electronegativity between oxygen and carbon is 1.0. Now, carbon dioxide has a linear geometry. The dipole moment of one bond completely cancels the dipole moment of the other one, and the molecule is non-polar. Okay, so here we can write the polarity of the bond by using this type of arrow. Okay, we're pointing toward the one that is more has a higher electronegativity, and we can create like a cross in this side to represent the partial positive. At the same way, we can draw another arrow from right to left, representing the polarity of or the dipole moment of this bond. Okay, oxygen is more electronegative, carbon more positive. So we have one vector going to the left and one vector going to the right. So because they are going in different ways, they're going to cancel. And even though you have two polar bonds, the molecule is nonpolar. So that means that if you have a polar bond in a molecule, that doesn't mean necessarily that the molecule is going to be polar. We need to evaluate the structure of the geometry. So in that way, we can see if those vector they cancel or they basically add each other. So we can represent polar bonds with arrows, as I mentioned before, or vectors that point in the direction of the negative pole and have a plus sign at the positive pole, as we shown before in the carbon dioxide. If the arrows point in exactly opposing direction, as in carbon dioxide, the dipole moments cancel, making the molecule nonpolar, even though they have polar bonds. In the vector representation of a dipole moment, the vector points in the direction of the atom with the partial negative charge. So what about water? Let's try to use the same concept with water and see if water is polar or non-polar. Each bond is a polar because the difference in electronegativity between oxygen and hydrogen is 1.4. So that means that this bond here, remember this hydrogen, this is oxygen, we have a bond between these two atoms. So hydrogen is more positive than partial positive and the oxygen partial negative. So that means that we're going to draw a dipole toward the oxygen. And when we see the other bond is going to be the same concept, we're going to draw a vector, okay, from positive to negative. So we have two dipole moments and that they not cancel between them. So that's why the molecule is polar. They're going toward the same point. Okay, so that means that water is a polar molecule. So we're going to show you here a few examples based on geometry. So when we have a linear geometry, they're going to cancel between them. So the molecules are going to be non-polar. If we have, for example, the trigonal pyramidal, they're going to point downward. Okay, so in that way, they will not cancel between them. So the molecule is going to be polar, as an example of NH3. NH3 is going to be a polar molecule. If we have, for example, this type of rearrangement, this is a tetrahedral. All of them are going in different way, but they will cancel between them. So that's why a tetrahedral is going to be non-polar. If the geometry molecule of the geometry molecule of a molecule is tetrahedral, that one is going to be non-polar if the uh, dipole moments of all of them are the same. Here we have the trigonoplanar. They also have three identical polar bonds at 120 degrees from each other, and they're going to cancel between them, so that's why it's going to be a non-polar molecule. And here we're going to have the bent. They're pulling each other apart, but they are not going to cancel between them. So this type of molecule is going to be polar, the bent one. And in all cases where the polar bonds cancel, the bonds are assumed to be identical. That's why I mentioned here that it has the same dipole moment, because if this has a higher dipole moment than this one, maybe you're gonna have a partial polarity there. But we're assuming here to be nonpolar that all of them are identical. So going back to our initial question of this section, why oil and water don't mix? Water molecules are polar. The molecules that compose oils are generally non-polar. Polar molecules interact strongly with other polar molecules because the positive end of one molecule is attracted to the negative end of another one, just as the south pole of a magnet is attracted to the north pole of another magnet. A mixture of polar and nonpolar molecules is similar to a mixture of small magnetic and non-magnetic particles. The magnetic particles clump together, excluding the non-magnetic ones and separating into distinct regions. Similarly, the polar water molecules attract one another, forming regions from which the nonpolar oil molecules are excluded. So here we have the magnet, the south pole and north pole, they attract each other. Here we have an example. This is known as a hydrogen bond between this partial positive and this partial negative. They're going to attract each other. Okay, so in that way, they're going to start to build that interaction between those polar molecules. Removing from them, those are unpolar. So that's why we saw two faces basically in when we try to mix water and oil. Okay, the oil molecules are non-polar, while the water molecules are polar. So they're going to start to attract between them, removing and excluding those molecules that are non-polar. So polar and nonpolar molecules, they don't mix. That's why the reason why they don't mix. Now, how soap works. After eating a greasy cheeseburger, your hands are coated with grease and oil. If you try to wash them with only water, they're gonna still be greasy. However, if you have added a little soap, the grease washes away. The question is why? Now, water molecules are polar, and the molecules that compose grease and oil are nonpolar. So why what has a soap that can somehow remove those grease molecules with water? So the molecule of the soap is this one. It's going to have a polar head and it's going to have a non-polar tail. So the polar head is going to interact with what? If you have water and oil, it's going to interact with water. While the non-polar tail is going to attract the grease. So this is going to be like this how you call it? It's going to help to bond together these two molecules that are not related between them about with polarity, okay? Because this end is going to help to attract the polar ones, while this one is going to help to attract the non-polar. So the polar head of the soap molecule strongly attracts water molecules, while the non-polar tail strongly attracts the grease and oil molecules. Soap allows waters and grease to mix, removing the grease from your hands and washing it down the drain. So that's how the soap molecule works. Okay, it's going to help us to mix those polar and non-polar molecules. So, in a review of chapter 10, the Lewis theory, the chemical bonds are formed when atoms transfer valence electrons, ionic bonding, or shared valence electrons, that are covalent bonding, to attain noble gas electron configuration. Molecular shapes, the shapes of molecules, can be predicted by combining Lewis theory with the valence shell electron pair repulsion, the VSEPR theory, where electron groups around the central atom repel one another and determine the geometry of the molecule. Also, we talk about electronegativity, that refers to the relative ability of elements to attract electrons within a chemical bond, okay, covalent chemical bond. Electronegativity increases as you move to the right across a period in a periodic table and decreases as you move down a column. When two nonmetals atoms of different electronegativities form a covalent bond, the electrons in a bond are not evenly shared and the bond is polar. In diatomic molecules, a polar bond results in a polar molecule. In molecules with more than two atoms, polar bonds may cancel, forming a nonpolar molecule, or they may sum, forming a polar molecule. And this will be all for Chapter 10, Chemical Bonding.